my name is Joe Vasta, and today we are going to talk about calculus and how it relates to a bug on a number line. So we start off with this function. It's a position function, and it tells you where the bug is on the number line. We'll use seconds for time and feet for position. And suppose you plug 1 second into that function. S of 1 gives you -1 squared plus 2 times 1 plus 1. That gives you 2 feet. So the bug happens to be at the 2-foot mark on the number line. Not -2 feet, but 2 feet. So if you're thinking of a normal number line, it's 2 feet to the right of 0. Well, what happens when you take the derivative of the position function? You end up getting, in this particular example, -2t plus 2. Well, that is the velocity function, or the instantaneous velocity function. And you can plug like 5 in there. V of 5 is -10 plus 2, so -8 feet per second. And that's what's happening at 5 seconds. So it tells you the bug's velocity on the number line. Now you take the antiderivative of the velocity and you get back to the position. So that's the deal with derivatives and antiderivatives. And this video is designed probably for people who've already had one semester of calculus, because we'll be showing you derivatives and antiderivatives. So let's move on. There are the graphs of the position function, that being a parabola, and of the velocity function. And yes, I do have negative time over here. When negative time just means like what happened like 1 second ago or 2 seconds ago. And so it makes sense to me. We have this question. Well, what is the instantaneous velocity at time 0? Well, the instantaneous velocity at time 0 is just v of 0. So let's take a look at this graph. V of 0 is you plug time 0 in and see where the graph is. The graph is right there at 0, 2. So that happens to be that point right there, which is the v-intercept. So 2 seems to be the answer for the instantaneous velocity, 2 feet per second. Let's take a look at how the instantaneous velocity is related to the position function. Well, we go to time 0 and we have a point there on the parabola at time 0, and we'd like to know the derivative at time 0, which represents the slope of the tangent line. So there is the tangent line, which has slope 2. So the answer to the question, what is the instantaneous velocity at time 0? We have 2 feet per second. And so we looked at it from the point of the velocity graph and from the point of the position graph, but it gave us the same answer, the answer 2. So now let's take a look at the next question, the rest time. Well, what is the rest time when the bug is traveling on the number line? The rest time is when the velocity is 0. And the velocity is 0 when the velocity graph crosses the t-axis, which would be at this red point, 1, 0. So the t-intercept being 1 answers the question. 1 second is the rest time. Now, if you're taking a look at the position function, we'd like to know when the velocity is 0, that's when s prime is 0, and that's when the slope is 0. So slope of the tangent, do we see any points where the slope of the tangent is 0? And that would be at the very top of that parabola, which corresponds to 1 on the t-axis. The slope of the tangent line is 0 at t equals 1. So our answer is 1 second. And we just want to interpret these things in terms of the velocity graph and the position graph. Moving on. What is the displacement of the bug on the number line in the time interval from 0 to 3? Well, let's take a look at the velocity graph first. And the displacement from 0 to 3 is represented by this definite integral. The definite integral represents a net area. The net area goes from 0 to 3, and it looks like this. It's the area between the graph and the t-axis. If it's above, which is blue, it's positive. If it's below, it's red, and that will be negative. So the area of the blue triangle is 1/2 base times height. You get 1. The area of the red triangle, you do the same thing. You get 4. Of course, that's going to be a negative area when you're looking at net area. Net area is -3. So here's the deal. Another way of looking at the displacement is s being the position, s of 3 minus s of 0. This right here is the fundamental theorem of calculus. And let's take a look at this graph here. What this graph does is it shows you what the bug is doing on the number line, and it might be best to think of the number line as the s-axis. So the bug is on the s-axis. He is at 1 on the s-axis, and then this tells you where the bug goes. After 1 second, he's at 2. So really, the bug, look at the blue thing. He goes like this. So at 1 second, he's here, and then as time is ticking, by the time it's 3 seconds, he crawled down to -2. So let me just draw a little diagram right next to the s-axis. It looks like that. So it tells you that the bug goes up and then goes down. And so the displacement from that little picture is really taking a snapshot. Take a snapshot at 0 seconds, which the bug is right here, and then take a snapshot at 3 seconds, which the bug is right here. And so that gives us -3 feet. That's the s-axis displacement. And so it looks like the answer to our problem is -3 feet. But once again, it's very interesting to see displacement in terms of the position function and its graph, and the velocity function and its graph. It's amazing. Let's move on. The next question that we're going to get is, what is the bug's average velocity in the time interval from 0 to 3? Now, you may have remembered from calculus that the average velocity is the displacement over the time. But in terms of the velocity, what it's going to be is the average value of that function. And so you might have remembered from calculus the average value of a function, on an interval, and that's what we're doing. We go 1 over, and this sometimes in calculus books is b minus a. And so looking at this picture here of the velocity, there's the average altitude of the line segment. It is -1. it's sort of the middle point. There are infinitely many points on this line segment, and if you average out, take the average altitude, you end up getting -1 for that. So the average velocity, I said, was the displacement over the time, and we're looking at this part of the parabola from 0 to 3. And this actually looks like rise over run of the points 0, 1, and 3, -2. And that's really what it is. It describes the slope of something called the secant line, and the slope is -1. So whether you're interpreting the average velocity from the velocity graph or the average velocity from the position graph, you get -1 feet per second. Also remember that the average velocity is always going to be over a time interval, whereas the instantaneous velocity, which this describes, this function up here, will always be at a particular time. Let's move on to the next problem. Well, it looks like we still have some things up from the last problem, and I did that on purpose. What we're looking at is the mean value theorem. At what time in this time interval from 0 to 3 does the average velocity, which is -1 feet per second, equal the instantaneous velocity? Of course, there's conditions on the mean value theorem like continuity and things like that, but we're just trying to make this, simplified. And what we want to do is we want to know when the average velocity equals the instantaneous velocity. Well, we know the average velocity is -1, and so what you would do algebraically is set v of t equal to -1. And of course, you can do the algebra on that, but I'm just looking at the pictures. We already have the velocity graph, and we want to find the point on the velocity graph that has a v coordinate or a second coordinate of -1. And there it is, the point is right there. Well, what's the t coordinate? That happens to be 1.5. So 1.5 is the time that satisfies the mean value theorem. It is in that time interval. It's between 0 and 3. So there's the mean value theorem. Now what I think is the mean value theorem is even more interesting over here on the position graph, because you have the secant line that's drawn from time equals 0 to time equals 3, and it has a slope of -1. And what the mean value theorem says is there should be a time between 0 and 3 where the tangent line at that point has the same slope as the secant line. They're parallel, and it looks like there is. That green line there. Let's go ahead and draw a little line down to the t-axis. That looks like 1.5. So the answer to this question is 1.5 seconds. And what does this mean? If you took v of 1.5 and you put it in to that function, so it's v of 1.5, you might want to go 3/2. It might be easier to put in there. You would end up getting -1. And that's where the instantaneous velocity equals the average velocity. Mean value theorem, if you care about the mean value theorem. Our last topic. Well, this is going to be the total distance traveled on the time interval. And the total distance traveled on the time interval, well, in terms of the velocity graph, it is the definite integral from 0 to 3 of the absolute value of the velocity. Well, there's probably a better way of thinking about that. And let's go ahead and draw our little triangles again. The best way of thinking about this is the total area of those triangles. Of course, I can do an absolute value of the graph, and then it takes everything that's below and puts it above, but I'm going to go ahead and look at total area. And so we have 1 there, and 4 there, and the total area is 5. That is the total distance traveled by the bug on the number line. Now, how would you do this if you just had perhaps the function s? You would do the displacement from 0 to 1 plus the displacement from 1 to 3, take the absolute values and add them. Well, where did we get that 1? The 1 is the rest time where the bug possibly turns around. So looking back at the position function, that's how the bug is traveling. The total distance traveled is this right here. He goes from 1 to 2 on the s-axis, and then he goes from 2 to -2. So, you have 1 first and then plus 4, which gives us 5, and we'll illustrate that. So first he travels 1 up and then 4 down. And so that gives us the s-axis total distance traveled of 5. And so looks like our final answer is 5 feet. I hope you enjoyed this video. Have a good day.